Hello, everyone. My name is Shatyakinan. This is a work with my advisor, Dr. Swastik Brahma, Dr. Lauren Nanjila, and I'm here to present our paper. And the title of the paper is Optimum Auction Design with Malicious Seller. Before I jump into the topic, I want to give a brief introduction of our work, then go into depth of how we design the auction. Let's introduce our topic. So nowadays, this hardware Trojan threats has been causing severe consequence in the Internet of Things world. Currently, as estimated, till 2020, almost 26 billion devices are connected via Internet of Things. So, under such circumstances, the hardware Trojan attack can cause severe impact in the communication system in Internet of Things. What the hardware Trojan can do? The hardware Trojan can leak sensitive information. Suppose, for example, when one device is connected, is trying to communicate with another device, under such circumstances, if the hardware Trojan threat attacks are happened in one of the devices, that device can disrupt the communication system between the two devices. The second reason, degradation of system performance. Third, the complete failure in achieving the organization goal. For example, in a military system, when two communication is going on between sending some information to the target, under such cases, if hardware Trojan attack is caused, the goal of taking the information to the particular target can be misleaded or can be damaged. So to do that, in such scenarios, the Trojan attacks has to be stopped. Otherwise, the Internet of Things communication can be in serious jeopardy. So let's give a brief introduction of the hardware Trojan and then our contribution of our paper. So hardware Trojan is actually a malicious modification in the integrated circuit. Such malicious modification, as I just gave in brief introduction earlier, can cause leakage of sensitive information, the performance degradation of computing platforms, the destabilization of military system. In the past, some of the defense techniques has been seen to detect, to find out some of the testing strategies, but we have to be mindful that exhaustive testing of all possible Trojan are prohibited. It can be due to cost issues, okay? Because if we are trying to test all the ICs, then undergoing such cost is huge. So we somehow have to figure out some strategies to actually pick and choose certain ICs. So how we do that? We actually use game theory to actually optimize or strategically choose certain IC to test the presence of a Trojan. One thing we also have to be mindful that testing is actually an error-prone process. So we have to design some different mechanisms which can go beyond testing and can optimize the system performance. So which brings us to our contribution. So what our goal in the paper, we are trying to employ the reverse game theory or the mechanism designed to mitigate threats from Trojan. So what we have done is we developed an optimal auction mechanism design where there are n number of sellers, where some of the sellers can be malicious in nature, and under such circumstances, we try to find out what will be the optimal goal of such buyers in the presence of such malicious seller. Second, we also employ the concept of redundancy to actually optimize the performance in the auction under such hardware Trojan threats. Thirdly, we also encounter the imperfection in the process of testing IC. So as we know, when we are trying to test this IC, under certain probability, the test will be successful. We have encountered such circumstances also, And taking such circumstances, we also characterize the optimal fine imposed by the seller upon detecting a Trojan in its sold IC. So with that, let's jump into our system model, what we have done. So here, what we can see that there is a set of n seller 1, seller 2, seller n-1, and seller n. Here, what we can see is some of the sellers are malicious in nature. So let's say seller 2 and seller n-1 are malicious in nature. Under such circumstances, each seller actually provides a valuation TI, and where A of I denotes the lowest possible valuation, and B of I denotes the highest possible valuation. So each valuation or each bit from the seller is being received by the buyer. So what will be the job of the buyer? The buyer views each seller to be malicious with a probability alpha, and every seller can insert a Trojan to its sold IC with a probability P. So what the buyer does after acquiring some IC, does some testing. So since we have encountered imperfection in our model, so with a probability PD, the Trojan can be detected. And 1 minus PD, the Trojan cannot be detected. So and also we consider if the Trojan is detected, there is a fine which is been imposed to the malicious manufacturer, which is donated by G of I. And if the damage caused from using the ICs have not got detected, then the buyer has to undergo a damage V of I. Then if the benefit which the buyer gets, if acquired some IC which is Trojan free, it gets a benefit BS. So now, what will be the goal of the auction of the buyer? The buyer holds an auction where what it does, it tries to figure out which seller to choose, which is given by this set of function, which is Q of T, which is actually a Boolean variable 0 or 1. Either I select the seller 1 or don't select the seller 1, which is actually the selection state of any seller I. Then one thing the buyer has to figure out, like how much payment it has to make to the seller when it actually purchases some IC, which is given by the term M of T, which determines the payment of seller, where M of T is the payment made to the seller I. So now what will be the goal? So now the goal of the buyer is to figure out what will be the Q of T, which sellers to choose, and how much payment to make, such that their expected utility is maximized from the auction mechanism while satisfying certain constraints. In this paper, we also encounter the concept of redundancy to optimize our performance. So what we have assumed that the buyer does not purchase or acquires not one IC from one seller. It acquires multiple ICs from multiple sellers, such that if one of them is having a Trojan inserted, then the buyer can use other IC to work with it. So let's see our optimization problem. So what we are, as I just explained, like the buyer's goal is to maximize the expected utility under Q of T, which is which sellers to choose, the Q of the selection state, and how much payment to make. And it is subjected to certain constraint. The first one is the individual rationality constraint. It says the buyer cannot force the seller to participate in the auction. What that means, if the seller does not participate in the auction, the expected utility of the seller will essentially be 0. So that's why we have considered that it has to be greater than equals to 0 for all sellers. The next constraint is the incentive compatibility constraint, which is what it means is that buyer cannot prevent a seller to put a falsified bid. So the seller can put a falsified bid, which actually increases its expected utility, which the buyer cannot force. That he or she cannot force the seller to not allow falsified bids. There can be scenarios like by doing that, the seller is maximizing the utility function, which is given by this constraint. Then the selection state. The selection state, as I just explained, which is a Boolean variable. Either you get selected which seller to choose, or this seller will get chosen, or this seller will get chosen. It is a Boolean variable, or either you get chosen or not chosen. So that is given by 0 or 1. Then the last one is very interesting one, is the redundancy constraint. What happens is the buyer actually, as I explained, the buyer acquires multiple ICs from multiple sellers. Here, what we have generalized is like the buyer redundantly gets from these sellers to enhance the chances, which actually enhances the chances of getting a Trojan-free IC, which actually maximized. So that's why the buyer acquires multiple ICs from multiple sellers, which actually helps the buyer to maximize the utility function. And we want to see in our theorem, in the next slide, the impact of this redundancy, how it helps in the auction mechanism or auction outcome. So let's next look at the theorem. So the theorem says for any Q and M, Q is actually the selection state and M is the payment. To be an optimal auction, Q should maximize this particular function, which is actually subject to the selection and the redundancy constraint. And we figure out that the payment made to the seller I, which is given by this particular set of equation. Now, let's see the impact of maliciousness in the auction outcome. What we have plotted is the average number of selected seller versus the Trojan insertion probability P. What we are able to see is that as we increase the Trojan inserting probability, the average number of sellers selected increases. However, one thing we need to see is like for a given PD, that is when the PD value is high, we can see the average number of selected seller is higher than when PD is 0, which we can see the pink line. Why? Because when the PD is high, that means that the buyer acquires most of the ICs which is not having any Trojan inserted. Thus, which actually justifies the payment made by the buyer that, okay, we have purchased a Trojan which is not having any Trojan inserted in the ICs. So for higher PD values, when PD is 1. Next, we have plotted the expected utility of the buyer versus the Trojan inserting probability. Here, what we are able to see, like as we increase the Trojan inserting probability, it is obvious that if the Trojan been inserted more and more in the ICs, the expected utility of the buyer will actually decrease because whatever the Trojan is being acquired by the buyer is having some certain Trojan inserted. So that actually decreases the expected utility of the buyer. However, one thing again to be noted, like when for higher PD values, so when PD is more, we are able to see the expected utility is higher than when PD is less. Why? So as I just explained, it's because when PD is high, the buyer is able to justify the investment what he has made. That is, like it enhances the chances of getting a Trojan-free IC is more when the PD is higher, which actually says like, which actually justifies leads to the point that redundancies actually enhance the performance under hardware Trojan threats. Next, let's look at the simulation result, what we have found out. Here we have plotted the average number of sellers versus the detection probability of the inserted Trojan. Here, what we are looking at is like as we increase the PD values, that is detection probability, we can see that for a given P, the average number of selected seller increases. Right? As we just discussed earlier, like when the PD value are higher, the buyer is actually able to enhance the chance to find a Trojan-free IC among the acquired ones, which actually justifies whatever the payment what the buyer has made, or the investment what the buyer have made is actually justified. Like, yeah, this is the payment that I have made. It is actually good for my system. Next, we have plotted the expected utility of the buyer versus the detection probability PD. Here, what we are able to see again, as we increase the probability of detection, the expected utility of the buyer increases for a given P values. Why? Because as we just discussed, because when we increase the probability of detection, the expected utility of the buyer increases because for higher PD values, there is a high chance that the buyer gets an IC where the Trojan is not inserted in the Trojan. So that's why the expected utility of the buyer also increases. Thus, also it justifies, like, if the buyer is able to acquire more number of ICs for multiple sellers, there is a high chance that the buyer actually is able to get an IC which is Trojan free, and it also increases the expected utility of the buyer. Next, let's look at the plot of where we have plotted the expected utility of the buyer UB versus the number of sellers. Here, what we are able to see is, like, as we increase the number of sellers for a given P values, the expected utility of the buyer increases. Why? Because when more sellers are participating in the auction, there can be chance that the buyer is able to get a better deal of an IC for a lower payment, as well as the number of redundant seller increases. The buyer is able to get a better deal of the ICs, and which actually leads to the increase of expected utility of the buyer with the increase of N, which actually correlates, like what I just explained, is like, so here what we have plotted, the total payment made by the buyer versus the number of seller. Here, what we are able to see is, like, when more sellers come into picture, that since the buyer is able to get a better deal or better deal of an IC in a lower payment, the payment made by the buyer also decreases for a given P, which actually again takes that to the point, like how redundancy helps in the system in this auction mechanism design. Like when we're trying to acquire more number of IC from multiple sellers, which actually enhances the performance of the buyers. So with that, I would like to conclude the presentation. So in the fabless semiconductor industry, a serious threat from the malicious insertion of hardware Trojan, it faces a huge consequence in Internet of Things applications, especially in the communication system. When one device is trying to communicate with another device under such circumstances, if one of the devices is having a Trojan inserted, you can imagine, like, maybe that device is able to retrieve information, leak to the third party, destroy the information, or do any kind of stuff. So for that, hardware Trojan attacks are very, very crucial to be stopped in Internet of Things world. What we have designed is a mechanism designed to actually mitigate from malicious seller. We all presented an optimal auction mechanism for trading with malicious manufacturer. We also employ the concept of redundancy to optimize the utility, as we just explained how redundancy helps the auction mechanism design. In the future, what we have planned is to investigate a repeated interaction between manufacturer and buyer, and also investigate IC testing in consideration of malicious ICs, malicious tester, where there can be multiple testers. Those are malicious in nature, and try to figure out what will be the optimal strategies under such circumstances. With that, I would like to take questions, and thanks a lot